Alright, so we are going to continue with mobile IPv6. Last time we did V4. So what is the difference from V6? So before that we will just go into what is V6. In particular we'll talk about the extension headers, neighbor discovery and so on and so forth. Then we go into what is the difference between mobile IPv6 and V4. And then there are 3 or 4 things which are unique to V6. We all know that V6 and V4 major difference is that V6 uses 128-bit addresses. And with 128-bit addresses, the first 64-bit are assigned for the network and then the last 64 for the host. And there are plenty of addresses available, so everybody can have a global unique address. I mean, global address as opposed to this, so there's no need for any private addresses. So here's the address. So 128-bit total, 64-bit of global routing prefix, 64-bit what we call network prefix, which consists of 2 parts, subnet ID and the global routing prefix. So this is what we call the network prefix, and then this is the host part of interface ID, another 64-bit. Generally this 64-bit is made up from MAC addresses. Anyway, so this is there are 2 bits in the middle, G and U. G means it is group ID and U is universal. So this is where a MAC address, if you remember the IEEE 802.3 or 802. Actually IEEE 802, not any point. IEEE 802 addresses are 48-bit addresses, right? The Ethernet addresses. And the first bit is multicast or unicast, group or non-group. So that's where that bit will go. And then U is the universal or local. So in Ethernet addresses, the second bit indicates whether this is an address which was assigned by IEEE, which is universal, or it is assigned by the organization owning it. You can assign a local address. So that is the non-universal address. So those are the same 2 bits here. So 48 bits will fit, and then 8 bits afterwards would be selected somehow randomly, and this first 8 bits. So let's see. And addresses are put into a hex :hex notation. So if you remember in IPv4, the addresses are written as what radix they use, hex or octal or what in V4? Decimal, right? So in V4 we use decimal, and then we put between those decimal numbers what we put? Dot, right? Actually the dot reminds that this is a decimal number because the dots are used in decimal numbers. Here it is a hex and it is colon. So when you see a colon, then you know that this is an IPv6 address with and written in hex. So even though number could be 0, 1, 2, you know that this is a hex number and not a decimal number. And only other notation is that if you see 2 colons, that means you can add enough zeros in those positions to make it 128-bit. So for example, this address which has 2 colons here, now we have specified 1, 2, 3, 4, 5 16-bit numbers. So 5 times 16 is 80 bits are already specified. Now we need to specify missing numbers are 3 more 16-bit numbers, right? So we put 3 zeros here, 0, 0, 0, 0, 0, 0, 0, 0, 0. So that's the notation. And there is one, so that is the major difference is the address type. Second major difference is that there is an extra field in the packet called flow label. So if you take a source address, a destination address, and the label field, and you combine those 3 fields, so the source address is 128-bit, The destination address is 128-bit, and the flow level field is, I think, 16-bit. You combine these 256 plus 16 bits, that combination indicates a flow. A flow is something like a TCP and some kind of application or group of applications. And so rather than looking into the port numbers as we do in IPv4 to find out what application it is, you can use as just flow level to determine a flow and not. It's basically, there are certain things that we cannot do to a flow. For example, we don't want to reorder the packets inside a flow, right? So you don't have to look at the port numbers, you can just look at this flow field. Second thing is it also has scoped addresses. So just like we have private addresses in IPv4, and the private addresses cannot get out of the organization. They have to stay inside the private region and they cannot get into the public internet. So here they have defined many more such boundaries, not just the public-private boundary. Inside the private network, you could have a link boundary, a site boundary, and so on and so forth. So there is something called link local. An address which is good only for that link, which means on that Ethernet. As soon as it gets out of that Ethernet, the first router will block it. Site local. Site local is it is good for that particular site. So for example, Vashu has two sites, medical school and this is school. And then if there is a site local address, which will be identified by certain bit in the addresses, that address will only be allowed inside this site and cannot get out of this site. The routers on the boundary of the site will block it. And then they have extension headers. So they have lots of headers, which basically IPv4 has only one header, in which you have source address, destination address, and so on and so forth, many fields. But IPv6 has many headers, and some of these headers are optional. And so you can just use as many headers as you need for whatever application you have. So that the headers, if everything was required, then the header will become very big. And the address by themselves are so big that the header is already big because of just the two addresses. So they said, okay, we will have lots of optional headers. Those are called extension headers. So extension headers could be a routing extension header, hop by hop extension header, and destination option extension header. As the name indicates, the routing extension header is used for routing the packets. Maybe you want to specify source routing. Hop by hop extension header is changed at every hop. Destination option header is only used at the destination, and not looked up along the route. So anyway, it turns out much of this we will not be using, even though this is these features are there, but we might use an extension header or two. But other than that, these are just general introduction to IPv6. Second common thing is in IPv4 we need DSCP. DSCP is the Dynamic Host Control Protocol. What does DSCP do? Assign the address on the IP address on the network, right? So that is allowed in IPv6 as well. However, you can do yourself. You can generate an address yourself and use it. So you don't need a DSCP server, and that is called stateless. Stateless host can make a global address using the advertised network prefix, and then the network identifier should be unique. So basically the interface identifier should be unique. So using their MAC address and the network prefix which has been advertised, you can make up an address which is unique to you, because nobody else has that MAC address. MAC addresses are globally unique by design. So that is another thing, is that you could generate your own address, and it is called stateless because nobody remembers it. I mean, the thing is, in the case of stateful, DSCP has to remember that I assigned this particular address to this host, and in fact if you reboot your router in the middle of something, the router may assign your address to somebody else. Generally it doesn't happen, because the reason it doesn't happen is because generally when you request an address, from DSCP, you give a preferred address. You say, well, can I get 104? Because that was your address before, right? See, huh? No, the lease is forgotten. The thing is, when you reboot the DSCP server, the lease is forgotten. It doesn't remember that I had given, unless you have a router which has some memory in it, but most of the routers will not remember what they had leased out. Not over the reboot. They will remember if they are up all the time. But if you reboot them, then somebody else can get the same address, but it doesn't generally happen because the requester has not rebooted. If both requester and the DSCP server is rebooted, obviously this can happen, but then it's not a problem. So the point is that the DSCP server has to remember what address they had given to whom. So it is stateful, and if the state is lost, there can be some conflict. Okay, two hosts may get the same address because one is having the previous lease, hoping that the lease has not expired, and the new one has been given to somebody else. You understand? And so sometimes you get a message on your computer, and I don't know how many of you have gotten this message, but sometimes you get, well, there is an address conflict on the network. Right? And that means that your computer has the same address as somebody else, same IP address as somebody else on the same network. And in that case, all you have to do is release the address and basically ipconfig command. ipconfig / release and ipconfig / renew. When you go to renew, you get the new address, which doesn't conflict. Okay? So this is called stateless and stateful. All right. So what is the difference between mobile IPv4 and mobile IPv6? So first thing is that there is no need for a foreign agent. The reason you don't need a foreign agent because care of address, you don't need a care of address because you have a globally unique care of address. You can make up your own globally unique care of address. So you just basically it comes directly to you. Second thing is route optimization. Is that you do not have to go everything through the home agent because then everything is a triangular. You know, if your correspondent is next to you, you can go directly. Now here it turns out that all of these optimizations can be extended to IPv4. So it's not that IPv4 is missing something. It's just that they're discouraging to make these to IPv4 because so that IPv4 basically goes away, IPv6, there is reason for it come up. I mean, IPv4 can also do route optimization, but there we didn't do it, and we said, well, we don't want to have local location privacy being violated. So route optimization does violate the location privacy when you do that, but basically you can do it selectively in the sense that you could do only with the correspondents with whom you want to tell them location. Secure route optimization, and then and we will talk about that briefly later on, is that you could do it so that when you are, one of the problems is if you're not going to go to home address, somebody else could say, well, I am Rajan from Vashu, and then here is my foreign address and so on and so forth, and please send me all your packets. And then somebody wants to say, wait a minute, are you really from Vashu? How do we verify that? So that is the secure route optimization. New extension header in place of tunneling. So tunneling means putting two full headers. Remember, what was tunneling was encapsulation. So you had the IP packet with full IP header, and you put another full IP header on the top of it. That we don't need here because we have extension headers. So we can just add a little extension header and whatever extra information is required, we can put in there, so it is less overhead. And then neighbor discovery in place of ARP. Now ARP is address resolution protocol. Anybody remembers what ARP is used for? Yeah? Yeah. So if you want to find out the MAC address for IP, or actually the other way around as well. If you want to find out the IP address for a MAC, you can use ARP. So you can send an ARP request saying that generally, I mean, if you have the MAC address and you want to find IP, you may just send to that MAC address, but you could also send a broadcast request. So you could just send who has this IP address, and then somebody, hopefully that node with the same IP address and MAC address will tell its MAC address, right? So that is R. So a generalization of that is what we call neighbor discovery, to find out who has the layer 2 address. So this is more general than just Ethernet. So that is called neighbor discovery. Dynamic home agent discovery returns a single reply. And the second and the final thing is that dynamic means time changing. So whenever you want to find out who can be my home agent, you get a single reply rather than infinite replies. Everybody saying that I am a home agent and I can be your home agent. So those are the 6 major changes, and we will go through them one by one. So first thing is binding update. So what is a binding? A binding is registering with the home address, home agent. So basically what you register, you say to home agent, look, here is my care of address. Any packets coming to my home address, please send them to this care of address. So it has bound that your home address with your care of address. That is binding, right? And every time you change that binding, that is a binding update. And so in IPv6, there is a new extension header. There is a new extension header which is called mobility header. Type 5 means it is a binding update. Each binding update has a sequence number, and the mobile keeps track of the last sequence number for each destination. Home agent performs duplicate address detection, updates the binding cache, and sends the binding ACK. So basically, you send that, okay, here I am, and then the home agent will make sure that this address is not a duplicate address, in the sense that somebody with that address is not already present in the local network. I mean, it's quite possible that you are saying that you are in Germany, but you are also in Washu. So now there is a conflict. There are 2 copies of you, right? So that is why the duplicate address detection is required. So before it registers, it sends a packet in the local network and makes sure that nobody answers it, and then it updates the binding. So this is just double checking that it's not a false, it's not, okay. And then second thing is no network entry, new network prefix, and default router unreachable. So basically what happens is when you move, your host part remains the same, but you get a new network prefix because you are in a new network, right? The network prefix has changed, and that becomes your care of address. And then so you accordingly change. Basically you have to find the new default router. Default router will depend upon the new network prefix, and so those are the things that you have to do locally to be able to send the packets under that network prefix, under the new network prefix. So you have a new, because everybody has this host part which is somewhat globally unique because it came from the MAC, and then the network prefix which is unique. So basically you can make an address and start using it, right? So basically some of the things that the foreign agent was doing are not really required here, and you can do it yourself. The second thing is route optimization. Previously we used to go back, so the correspondent will always send the packet to the home agent. Home agent will always re-encapsulate the packet and send it to the mobile. Mobile will send a double encapsulated packet to the home agent. Home agent will take out the encapsulation and send it to the correspondent. That is how it was in IPv4. In IPv6, you can just do directly like this. After you get your first packet, you can tell the correspondent, look, I am right here, and this is my new address. You can send me that way, and then you can just talk to each other directly. So you don't have to follow this triangular path. And the way you do that is that you can put an extension header in which you keep the other information. So for example, the packet as it comes from the higher layers, it will have TCP, whatever the TCP packet is, and on the front of it we will put the correspondent address, which is the source address for the correspondent, and then the destination address is HOA. So the packet will come like this, okay? It will come to it is going from the correspondent to the home agent, to home address. However, the IP layer, IPv6 layer, will add a field here. It will put that new care of address here. This is a destination option header. So this is one of those, remember the extension headers, which is destination option, it is only looked at the destination. So the intermediate routers will not look at this header because they know that this header is only for the destination. This is in the IP layer, but the routers don't have to look at all the headers. They only look at the headers which are designed for routers. So this is destination option header, and this has the care of address. So now the packet is destined to the home address. So obviously if this packet remains like this, it will go to the home address, but we don't want to go there. So then after that, the IPv6 layer will switch these two. It knows that this is a mobile IPv6. So on the wire, by the time it gets to the MAC, the packet looks like this on the media. It has the correspondent address as the source address. It has the care of address as the destination address, and the home address goes into this field, destination option header. So they have switched. Alright, so now this will be correctly delivered directly from there to there. Why? Because the destination address, as soon as it got out of the host, here is actually the care of address. And the mobile IPv6 does that switching. Now, in the reverse direction, same thing happens. Mobile node response, actually before all this works, actually you will have to do that mobility binding, as we said, that mobility binding. One thing I should have mentioned here, the mobility binding you can do not only with the home agent, you can also do with the destination. So you could, just like you register with your home agent that I am at this hotel, you tell your correspondent that look, I am at this hotel. So the same message can go there, and then they will remember all this care of address and so on and so forth. Right? So the mobility binding is a general name which can be sent, and that's why it has to remember for each destination it says. So every place you send, you know that what I told them. Anyway, so it sends this packet. Well, again, I mean, you can start the other way around. Basically, the source address would be home address and CN address and so on and so forth, and packet on the media will look just basically such that the addresses are correct, and the home address gets inside. So basically, the packet will always look like having the correct source and destination address. All right, in both directions. So let's read these lines again one more time. So shortest path in both directions. That's what we are doing. Mobile sends a binding update to the correspondent. So the mobile sends the binding update, so therefore it knows the care of address, and it can do all that substitution there. And then the new destination option. So there is this destination option in which there is home address can be put and the care of address can be put. So HOA option is used in all packets. Correspondent replaces the SA with HOA before passing to the upper layer. So when it goes up, the reverse happens. When the TCP receives the packet, it receives like this, and it will basically, it doesn't really know that it came through mobile IP. The TCP will think that the packet came with the source address of CN, the destination address of HOA, and rest of the TCP. So it is kind of invisible to TCP. It is just basically TCP doesn't have to worry about whether it came through mobile IP or regular IP. The mobile IP layer will take care of itself and switch the addresses correctly. just this slide actually gives a little bit more detail of the header types and so on and so forth, but exactly we have finished the discussion on this anyway. Is that the source and destination options are interchanged before transmissions and after reception. In the reverse direction, the header type is routing header type 2 that contains the home address, and the destination and the addresses are changed before transmission and reception, exactly same thing. And if there is no binding for it, then the binding error message will be sent. So for example, here somebody is trying to send this packet, and then the mobile IP doesn't know the care of address, then it will return binding error. Now, so what is the advantage of this, putting the address here? See, if you remember in the IPv4, we do something similar, but actually this is your original packet and this is your encapsulated packet, right? So the original packet, we have not completely put the whole header, we just have this address and that's it. And so basically this is shorter than what it would have been if it was in IPv4. In IPv4 we complete two complete headers. Here you only keep the important part of the header, which is the home address. Everything else is used here. So that's the thing. IP and IP tunneling will require 4 addresses, which in case of IPv4 will mean 4 addresses will mean 128-bit times 4. 3 addresses is a big optimization, 3 times 128-bit. Okay, so instead of doing full encapsulation, we use this special header and put the previous information there, and then so that we can use it at the final place. So 2 generalizations so far. Let me just review that. First of all, that you can send your registration mobility update to your correspondents, right? So if you're talking to 5 nodes, you tell them your new location in addition to home address. So they know your, so the location privacy is gone. I mean, obviously they know that you are what place you are in. Okay. So, but it optimizes the path, because if you are really in a far away from home, but very close to the, because generally what happens is when you are far away from home, you are talking more to the people in that area rather than talking to home people. And therefore, you end up, if you don't do this, then you end up taking a long route path. So there is a security risk here, because anybody can tell that I am in Germany, and then basically all my packets will go to Germany, and then they'll be thrown out there because I am not there. Right? So we have to verify that. I think that is the next one. Return routability procedure. Now, this slide goes with the next one. Unfortunately, this is a lot of security thing here. So I'm not going to really cover the security part, but this is, you can understand this very easily from this slide. So I'm going to explain, just intuitively as to how this all works. Is that when you say that you are somewhere else, we have to make sure that you are the same person who can also receive things at the home. So you have to send 2 pieces of information. One piece you send directly to the correspondent and say, look, I am here. Another piece of information you send through your home address. So something has to come from Vashu which says that Raj Jain is in Germany. All right? And then obviously the one direct message will go which will say, well, I am in Germany. And then something which has Vashu stamp on it, so then we know that, yeah, both places. If those 2 things both arrive and make sense, then we know, yeah, this is Vashu Raj Jain. Right? So that's what we do. So the mobile correspondent and the home agent. So mobile sends a message which is called home address test init. Initialization. Home address test initialization. This message is sent from the foreign place straight to the home agent, and it is encapsulated, as you can see from this thing here. It is encapsulated, so nobody can read it. I mean, basically it goes straight to the home agent, and then home agent unencapsulates that part and sends it to the correspondent. So half of the message came from via the home part. Other message, care of test init, you send directly to the correspondent. So other half came directly, right? Now, if these two halves have something in common or they pass some security test, then we know that these came from the same source, right? And the correspondent does something similar. It sends directly, so using this it makes a key and sends half of the key directly like this, and the other half it sends to the home address, which is encapsulated and sent to the mobile. If you get both halves, then you have made the key. You can make up the whole key. Once you have the whole key, then you can give the answer. You can say, oh, I got the key and here's the thing. If your key is wrong, obviously they won't understand anything and you won't get any responses. But if your key is right, then the encapsulation will be heard, understood, and verified. So you can say, well, I got it, and they will say, okay, we got it too. All right, so does that answer your question? Right, so what you do is you send two halves, one through the home, one directly, and then the responder also sends two halves, one through the home, one directly. If both of you get both pieces correctly, then you are in business, you can make up the whole key. Otherwise, you won't be able to do that. Now, in terms of security, it uses this SHA and HMAC and so on and so forth. Unfortunately, I don't think they have covered it, so I don't want to cover it for this purpose. But basically, there are techniques for message authentication and for hashing and so on and so forth, which are used to verify these messages. Okay? So I will not actually, I'm not covering the slide number 10, but slide number 9 you should be able to understand, and basically the whole key part of it is that there are just 4 messages sent, 2 from the mobile to the correspondent and 2 from the correspondent to the mobile. And then if both of them get the full piece, then they can send the update, authentication, and acknowledgement.